You know when you're streaming a 4K movie, someone else is on a video call, and another person is gaming online all at the same time, and somehow it all just works? Well, that's not magic. It's thanks to this invisible, absolutely brilliant system called Network Flow Control. And today we're going to pull back the curtain and see how it keeps our entire digital world from grinding to a halt.
And this quote here, it just nails the problem perfectly. See, in theory, sending a piece of data is simple, right? It's like putting a letter in the mail. But in practice, when you're trying to mail billions of letters every single second, you need a seriously sophisticated system to prevent a pileup of cosmic proportions.
So that's the big question, isn't it? With literally billions of devices all trying to talk at once, how on earth does the internet not just seize up into one permanent global traffic jam? Well, let's dive in.
To really get our heads around this, we're going to start with an analogy we all know and, let's be honest, hate: the dreaded traffic jam. You'd be amazed how much a packed highway at rush hour has in common with the flow of data on the internet. And that, at its heart, is what flow control is all about. It's not some central traffic cop directing everything. Nope. It's a smart, self-regulating feedback system that makes sure the cars, our data, entering the highway don't just flood the road and bring everything to a screeching halt.
Now, a really critical piece of the puzzle here is something called round-trip time, or RTT. Just think of it as the absolute fundamental speed limit of any network. It's the bare minimum time it takes for you to send a signal and get a response. It's a law of physics, and you just can't break it.
And this physical speed limit, it creates a huge problem. For that entire round-trip time, the computer sending data is basically flying blind. It's pushing data out onto the network with absolutely no feedback about the traffic conditions up ahead. It has to just hope the road is clear, even if there's a 10-car pileup just around the bend.
So you're flying blind. What do? Well, over the years, engineers came up with two fundamentally different philosophies, two different ways of coping with this potential overload.
On one side, you've got the lossy approach. This idea comes from the world of communications engineering. It basically accepts that, hey, sometimes a data packet is going to get dropped. It's like the postal service. Most letters get there, but one might get lost now and then. But on the other side, you have the lossless approach, which comes from hardware engineering. And in that world, a processor would never drop data. It's built on the idea that every single packet has to arrive guaranteed.
Okay, so within those two big ideas, there are different strategies for actually managing the traffic. You can think of them as specific rules of the road.
The first choice you have to make is this: do you book your trip in advance, or do you just hit the road and hope for the best? Open loop control is like reserving your own private lane on the highway. It's guaranteed to be clear for you, but if you're not using it, that whole lane just sits there empty and wasted. Closed loop, on the other hand, is what most of us do every day. You merge into traffic and you adapt. It's way more efficient.
And the next choice is, how do you even find out there's a traffic jam? Well, with implicit feedback, you only know there's a problem when you see the crash, or in our case, when data packets start disappearing. With explicit feedback, it's like having a traffic helicopter radioing down, hey, slow down, there's a big jam 5 miles ahead. It's proactive instead of reactive.
All right, let's stop talking in analogies for a second and look at two real-world systems that show these different rules in action. Let's make this concrete.
First up, there's a system called XON/XOFF. This is basically a digital stop sign. When the receiver's memory buffer starts to get full, it literally screams X off, which just means stop. The sender then has to slam on the brakes until it gets the all-clear X on signal to go again. It's super simple, but all that stop and go can be pretty inefficient.
Now, the other way to do this is a credit-based system, and this is much more like a toll ticket system. A sender is only allowed to send a packet of data if it has a credit, and that credit represents a guaranteed open spot in the receiver's buffer. Once the receiver deals with the data, it sends a credit back to the sender. This is great because it means the sender never sends data unless it knows there's a place for it to go.
And this is where you see the really clever trade-off. That simple stop sign system, X on, X off, it needs a huge emergency lane, a big buffer to handle all the data that's still in the mail, even after it yelled stop. But the more sophisticated credit system is way more efficient. It only needs enough buffer to hold the data that's currently on the wire at any given moment because it knows there's always a space waiting at the other end.
Okay, for our final act, we're going to zoom all the way in. We're going from these abstract concepts down to the actual physical hardware that makes all this happen. We're going inside the silicon brain of a network switch, the ASIC.
Get ready for a number it's going to break your brain. A modern network switch has to deal with something like 38 billion packets of data every single second. Think about that. That's more packets in 1 second than there are people on planet Earth. The scale is just staggering.
So what does a number like that mean? It means there is no single computer processor on the planet fast enough to do that job. It's just not possible. So the only solution is massive parallelism. You have to build a chip with dozens and dozens of smaller processing pipelines all working together at the same time.
So how do they manage the traffic inside the chip itself? Well, they use this beautiful, elegant trick. They take every packet that comes in, whether it's big or small, and they chop it up into these little fixed-size cells. It's like having a toll booth where it takes the exact same amount of time to process a motorcycle as it does a giant semi-truck. It makes the whole system incredibly predictable.
And the payoff for that one simple design choice? It's not small. It is absolutely huge. The math of queuing theory proves that by making the service time predictable, you cut the average length of the line in half, exactly half. That means less congestion, lower latency, and a chip that is just dramatically more efficient.
So, from the laws of physics and the speed of light, all the way down to the pure mathematics of queuing theory, we've seen just a glimpse of the incredible engineering that keeps our internet running. But, our demand for data is only going up, which means the next great bottleneck is always just around the corner. The only question is, what's it going to be?